Okay, so today is the last lecture in terms of all the things that we need to talk about for the unit on gases. We need to talk a little bit about stoichiometry problems and some other stuff that have to do with gases. It's a little bit longer, but we'll get through it as quickly as we can. Now, we're going to talk about how we can apply stoichiometry, the thing that we learned about last unit, to the ideal gas law, specifically when we talk about gases in general. So, first thing that we need to remember is that we always start a stoichiometry problem with a balanced chemical equation. So in this case, the balanced chemical equation says sodium metal, so that's solid, reacts with fluorine gas, that is a Brinkelhoff diatomic molecule, so it's going to be F2, to form solid sodium fluoride, which is going to be NaF solid. And then to balance this particular reaction, I need to place a coefficient of 2 here, a coefficient of 2 here, and a coefficient of 1 there. Now, I'm going to be using this particular reaction for the next few slides, so I'm going to take a second and cut it out and put it over on the next slides now. Okay, so now that I've got that squared away, let's take a look at our very first example problem. And we're going to do this in two parts. The first thing that we need to do is we need to identify that the problem is asking us what mass of sodium metal is needed to react with 1.75 liters of fluorine gas at 0.975 atm and 22 degrees Celsius. So the first thing we're going to do is we're going to use the ideal gas law to go ahead and identify our variables. And just like before, we had P, V, and RT, and I'm going to take a second to go ahead and fill these values in. So just like before, we have to make sure that all of our units are in the appropriate units, and I see that my pressure is in ATMs, my volume is in liters, my ideal gas law constant is in the appropriate number, and I need to change the Celsius to Kelvin by adding 273, and I get a value of 295 K. So I'm going to go ahead and set up my ideal gas law, which is PV equals nRT. And because we're looking for a mass, the only thing that allows us to get to a mass eventually is the mole quantity. So I'm going to solve for moles in this case. So I'm just going to kind of fill my variables in with 0.975 ATM, 1.57 liters, solving for N. We know that R is 0.0821 liters ATM per mole per Kelvin, and the temperature we determined was 295 K. So I'm going to basically do some multiplying and dividing and determine that the number of moles in this particular case is 0.975 times 1.57 divided by 0.0821 divided by 295, and I get a value of like 0.0632 ... and that's moles of the gas, which in this case is F2. So now that's my first step. So now that I know the number of moles, what I'm going to do next is I'm going to use the stoichiometry to convert from moles of F2 to moles of Na, which is what it's asking me to solve for, sodium, and then eventually to mass of sodium. So I'm going to take the 0.0632 moles of F2, and I'm going to consult my mole ratio, and this time my mole ratio is 1 mole of F2 for every 2 moles of sodium. So I'm going to set it up where I put 1 mole of F2 on the bottom, 2 moles of sodium on the top, and then I'm going to convert to mass of sodium, so I need to go consult the periodic table to get the molar mass. So in 1 mole of sodium, I know that the molar mass is 22.99 grams of sodium. So now I'm going to go ahead and just calculate this out. So I'm going to take the 0.0632 times 2 times 22.99, and I'm going to get a value of something like 2.906 ... And so to go back and assess significant figures, in my original problem, I had two significant figures for temperature. So I'm going to go to 2.9 grams of sodium is how much I would need to react with 1.57 liters of fluorine gas. Okay, so the next question says what volume of fluorine gas measured at a pressure of 1.1 atm and 35 degrees Celsius is needed to produce 10 grams of sodium fluoride. Okay, so first of all, I am trying to figure out how much fluorine gas I need when I know that I've produced 10.6 grams of sodium fluoride. So in this problem, I'm going to do stoichiometry first. So I'm going to take mass of sodium fluoride to moles of sodium fluoride to moles of fluorine gas. So now what I'm going to do is I'm going to go ahead and I'm going to convert that all the way through. So I'm going to take the 10.6 grams of sodium fluoride, which is NaF, and I'm going to convert that to moles of sodium fluoride. So in 1 mole of sodium fluoride, I have, let's see, sodium is 22.99, fluorine is 19. I get something like 41.99 grams of sodium fluoride. And then I'm going to consult the mole ratio between sodium fluoride and fluorine gas, which is still 1:2. So I'm going to put my 2 moles of NaF on the bottom and my 1 mole of F2 on the top. So I'm going to take 10.6 divided by 41.99 divided by 2, and I'm going to get a value somewhere in the ballpark of 0.12622 ... moles of F2. Now, the next thing I need to do is I'm going to go ahead and use the ideal gas law, which we know is PV equals nRT, because we're trying to figure out what volume. So PV nRT, we are looking for volume when we know that the pressure is 1.10 atm. We know that R is 0.0821 liters atm per mole per Kelvin. And we know that the temperature is 35 degrees Celsius plus 273. So 35 plus 273 is 308 Kelvin. And now the number of moles is going to be the 0.12622 ... from above. So I'm going to be solving for volume in this case. So what I'm going to do is I'm going to fill in what I know. I know that pressure is 1.10 atm. We're solving for volume. We know that the number of moles is 0.12622 ... moles. We know that R is 0.0821 liters atm per mole per Kelvin, and we know that the temperature is 308 Kelvin. So I'm going to take the 0.126 or 126 times 0.0821 times 308, and then I'm going to eventually divide that by 1.1. And I'm going to get a value for my volume to be somewhere around 2.90, 155 ... So then going back to 2 sig figs, that tells me my volume is somewhere in the ballpark of 2.9 liters of F2 needed, or needed. So that's not so bad. And then we have gas law, for example, that we're going to talk about real quick, and it's called the ideal shortcut. And so the ideal gas law shortcut allows us to do a couple of things that we can only do when we are at standard temperature and pressure conditions. So STP, remember we talked about this before, said that at the conditions of 1 atm, which is the pressure, and at 0 degrees Celsius, which is the temperature, those are the agreed upon standard temperature and pressure conditions. When we have that, 1 mole of any gas has a volume of 22.4 liters of that gas. So if you had me last semester, and I'm pretty sure Miss E gave you something similar to this, if we went from mass to moles to moles to mass, we go from mass to moles, we needed the molar mass, and we go from moles to mass, we need the molar mass, and then from moles to moles, we needed the mole ratio, we needed the mole ratio. But now, if we are at STP only, we can go from volume of a gas to moles. Only when we're at STP. And when we do that, we know the relationship there is that 1 mole of any gas is equal to 22.4 liters of that gas. And then I can also do the same thing over here. I can come off of moles and determine the volume of something that's a gas at STP. As long as, again, we are at standard temperature pressure conditions, and we realize that 1 mole is equal to 22.4 liters. So I'm going to show you kind of how that works. So in this case, I have a volume of fluorine gas measured at standard temperature and pressure conditions, and I'm trying to determine that volume, and when we react it with 15 grams of sodium. So the way that my head would work is I would say that, well, I'm going to go from mass of fluorine gas to moles of fluorine gas to, I should do that. I should say that again. I'm going to go from mass of sodium to moles of sodium to moles of fluorine gas to volume of fluorine gas. And I can do that using the mass, I can do that by going mass to mole to mole to volume. But that's only true because we're at STP. So I'm going to take the 15 grams of sodium, and I'm going to take the 15 grams of sodium, and I'm going to convert that to moles of sodium. So in 1 mole of sodium, I have 22.99 grams of sodium. And then I'm going to use the mole ratio. So sodium to fluorine is a 2-to-1 ratio. So I'm going to take my 2 moles of sodium for every 1 mole of fluorine. Now at this point, instead of going to mass of fluorine, I'm going to go to volume of fluorine, because I know that 1 mole of fluorine is equal to 22.4 liters of fluorine. So when I go ahead and plug this into the calculator, I get 15 divided by 22.9 divided by 2 times 22.4, and I get a value of 7.33 62 something something something, and to go to sig figs. Because this is a relationship, they have infinite number of sig figs, so I'm going to go back to my 3 sig figs, which is going to be 7.34 liters of F2. Now, if you use the ideal gas law, and you went mass to moles to mole, and then you plug that into the ideal gas law, you would get the exact same answer. Might be off by 100th or so of a gram, but it would be essentially the same answer. So that's it for this particular guy right here. Let's see, might need to talk about, I'll talk about this in another video, so it's not quite so long. So I'm going to stop here telling you that the gas law stoichiometry homework, which I believe is a 2-sider, will be due tomorrow. So good luck with that, and I'll be back with the rest of the notes in a little bit.